Okay, we are going to start. We have a pretty full schedule this afternoon. And so we're going to start with Javier Licandro, who's going to talk about TNOs. I think we can.
And the present population of Trans-Neptunians is composed mainly on the planetesimal that survived the accretion of the planet. When planets form, they basically accreted most of the objects or scattered them out of the solar system. In fact, we believe that we only have now in the Trans-Neptunian region about 3% of the mass that formed of the planetesimal that had been there when the planets were formed. So the initial mass was much larger. These are small objects in a very cold environment, far from the sun. So what we expect to find there is the most pristine material since the formation of the planets. So they have fundamental cosmogonical information. We have a lot of information of which materials and the states of the materials in the early formation of the solar system. And what can we do in the thermal infrared with Trans-Neptunians or other minor bodies? Basically, we can obtain two kinds of information. First is if we have this flux distribution, that one. Hello? Yes. Ahora me tengo que estar alto. Hello. By looking at the flux at different wavelengths, for example, this is an Spitzer spectrum of an asteroid. We obtained it. It is a candidate to be studied with a Marco Polo mission. You can fit to this spectrum different kind of thermal models. Marco will talk about this, and derive from them the size, the albedo, and the thermal inertia of any minor bodies, and of course, in the case that's the case of Trans-Neptunians. If we divide this spectrum by the model, we will obtain things like that. This is the emissivity spectrum. This is the emissivity spectrum of a Trojan asteroid. When you can see at 10 microns, this feature here that is typical of silicates, Umberto talked about a lot. And, for example, we can study this by comparing with meteorites or with silicate spectra obtained in the laboratory. So this is also a diagnostical spectral region for silicates. And in this case, we can use spectroscopy and photometry to do this kind of job. But what happened with Trans-Neptunians in the mid-infrared? Trans-Neptunians are very difficult in the wavelength range of CanariCam. Most of them are almost impossible to be observed with an instrument that goes up to 20 microns. Look at this is the flux distribution of some moderate Trans-Neptunian. This is 1,000 kilometer in diameter object. This is a very big Trans-Neptunian. At 20 astronomical units, this is unrealistic. There is no Trans-Neptunian such big at such a small astronomical such a small heliocentric distance. And look at the flux at 20 microns. This is 20 microns, right? This is a very rather low. It's possible to do photometry and maybe some spectroscopy. Yes, but if you want to do a spectrum, for example, with signal to noise 50, will be very, very 50 signal to noise 50. Okay, this is possible, but this does not exist. This is the typical case, right? That's hard. And for objects smaller than like 100 kilometers, this is the spectrum. So trans-Neptunians are very, very difficult. We can do some photometry in the Q-band of some of them. But, on the other hand, we also have a large program in the Herschel telescope devoted, that it is dedicated to observe trans-Neptunian. They plan to observe almost 130 trans-Neptunians in multi-band photometry. So, no chance, or very, very few chance, maybe some object that it is discovered after Herschel or things like that. So I had to finish. That's it. But that's not the case. We have other objects, other populations. For example, if you look at the dynamical evolution of one of the kind of trans-Neptunian we know, and scattered disk object, this is a plot of perihelion distance against, aphelion distance against perihelion distance. These regions here corresponds to trans-Neptunians. And the closest correspond, this is the Jupiter orbit, right? This region corresponds to some centaurs, this object between Jupiter and Neptune, right? So, look, this object that was trans-Neptunian evolves with time due to a gravitational interaction with planets, and at a certain moment start to be a centaur, and rise much closer to the Sun. And in a certain moment also crosses the orbit of Jupiter and become a Jupiter family comet, or a short period comet. This happened for a very short period of time, thousands of years, maybe 100,000 years, no more, and then escape again from the solar system. So we can observe comets that are in fact trans-Neptunians and centaurs. Umberto talked about comets. I will not repeat his talk. But we can also observe some centaurs. But again, only we have, as the centaurs we have are smaller than the big trans-Neptunian, the fluxes we can obtain are a very few millijanskis in the N band. In the N band, a little bit more in the Q band. We can do some photometry. No way to do a spectroscopy, but something can be done. But I know there is a program to observe centaurs with the James Webb that will do it much better. We can do some of them. We can try to observe, for example, new discovered ones. But this is not a very important program for CanariCam. Again, just quit. But that's not the case again. Because the remix of objects in the early solar system was so huge that we have a lot of trans-Neptunian coming that actually live closer to the Sun than the present trans-Neptunian. The dynamical modern dynamical models, like the NIS model, published in the first paper in 2005, indicates that when the planet just formed, there was a disk of planetesimals that remained that was much dense. We have much more dense than the present trans-Neptunian belt, and much compact than the present one. The planets here formed also closer to the Sun. This is Jupiter, Saturn. The blue one is not Uranus, it's Neptune. And the following is Uranus. And if you put this and let Newton work, this is what happens. In a few million years, about 800 million years, you will see that planets, the orbits of the planets expands, migrate, due to the interactions, the interchange of angular momentum with these, the trans-Neptunians that are closer, in particular to Uranus. The orbits start to expand, they move, and at a certain point, close to 800 million years, Jupiter and and Saturn are in the 2-to-1 resonance. And then this has a strong effect on Uranus and Neptune. The orbit of Uranus and Neptune will change a lot. Look what happened. Neptune was injected into the disk, also Uranus. They switch the position, and at present we have the solar system as it is, with Neptune farther from Uranus. And what the effect was that most of the objects here were scattered. And what we have now is the population that survived this scattering process. But this model also has some prediction that we can check. The first prediction that there should be a late heavy bombardment of objects. The moment during the 2-to-1 resonance injected a lot of objects, not only ejected a lot, but injected a lot of objects into the inner solar system, and produced a lot of collisions, in particular with the moon, that we know that exists before this model, and in the time expected, that is called the late heavy bombardment, also explain the existence of irregular icy satellites, and which is very important for us, predicts that all a kind of asteroid that are the D-type asteroids are all scattered trans-Neptunian objects that were injected into the inner planetary region a long time ago, about 4,500 years ago. So we have trans-Neptunians much closer. And this is what we want to study. In particular, these objects are in three populations. In the outer main belt. Right? This is the main belt of asteroids, between 2 and 3 something AU. And this limit is known as the Hecuba gap. And in the outer border of the Hecuba gap, you have a group of asteroids called the Cybele group. The Hilda group, that it is in a resonance, in a 3-to-2 mean motion resonance with Jupiter. This is a very stable region. The objects here are in a very stable orbit. And also the Trojan group, the Trojan asteroids, are in the Lagrangian L4 and L5 equilibrium point of Jupiter. So in extremely stable orbit. So these objects are there since long. Right? So if this model is correct, we have here a lot of trans-Neptunian objects moved there since long time ago. So if we can study these objects, we can obtain not only a lot of information on the composition of trans-Neptunian, but also it's a very nice test if we recognize them also because of their physical properties as trans-Neptunians. We have a very nice test for the dynamical models. So what we want to do is to do spectroscopic and photometric measurements, in particular in the 10-micron region, to study the silicate composition, derive albedos, derive size of this population. One very important thing, the trans-Neptunians are very competitive fields, but very few people is working in these groups, in particular in Cybeles and Hildas. So this is a project that can produce a lot of very new information that almost nobody is working on. What kind of information in particular? If we go to the wavelengths, easy wavelengths, let's say, for example, visible and near infrared, and observe the trans-Neptunian, we can see the trans-Neptunian have a lot of ices, the absorption bands, due to water ice, methane ice, and other ices. Here, for example, have two spectra of two big trans-Neptunian that show water ice. But when we look for the spectra, look at the spectrum of this primitive asteroid, we see what we used to see when we observed the trans-Neptunians some time ago. Very flat and featureless spectra. In the visible and near infrared, it is very difficult to obtain any mineralogical information of primitive asteroids because they don't have features. But the color, but the slope, we cannot say anything else. These are spectra we obtained of Trojan. These are spectra we obtained of Hildas, and these are spectra of comets. This is a comet. This is another comet, and this is a Damocloid that it is an asteroid in a cometary orbit that we almost have a 99% confidence that this is a dormant comet. That means a comet that is not active at all. And why do we observe this and not ices like you observe in the Trans-Neptunians, or in some Trans-Neptunians, at least in the big ones? That is because if you put an object composed mainly of ice in yellow and silicates in red, and exposes them to cosmic rays, the organics here, in particular the carbon chains, start to produce more complex organics and create an irradiation mantle that covers the surface. You don't see the ices. You will see a very red mantle of very dark, complex organics there. A few microns. 100 microns or less. Yes, it is very thin. You cannot penetrate much, right? And also, what happens when you put this close, an object like this, but close to the sun, like comets? The ice start to sublimate, and you have cometary activity, because the gases sublimated because of the heat also eject dust, but the largest dust particles are not ejected and remains in the surface and produce a dust mantle, right? And other process that happens also are collisions. That what happens if something collides with any of these mantle, just destroy it and show ices from below the mantle. So it's not surprising if we see that comets and Trans-Neptunians that are long-lived in the inner planetary region, because comet can activate easily at 5 AU, where the Trojans are, have developed a dust mantle, mainly of dust, of silicates, and some organics on them, right? And that is what we are observing. So, if we are able to do mineralogy of this, we will be able to obtain a lot of information of the silicates that compose the Trans-Neptunians. One way is to go to 3 microns. The 3 microns region is full of bands for ices and organics. Also, the 3 microns is very difficult. But, for example, if you have a very few amount of water ice, that's the case of asteroid Themis. If you look at this spectrum by Rifkin, and this spectrum we obtained also with the same instrument, the IRTF, you can see this band, and this seems to be water ice. We expected to see things like this due to hydrated silicates, but we surprisingly found water ice only 2 to 4% of water ice can produce this band of 3 microns, that it is not visible at all in the near infrared below 3 microns. Studies of Trojans have been done in this region, and by Emery and Brown, they didn't find any absorption band there. So they conclude that Trojan surfaces are mostly composed of anhydrous silicates. That is coherent with the dust mantle. In fact, we presented a proposal to observe this object, the Sibyllian Island Trojan asteroid, with NACO VLT. If any of you is in the panel, you consider that it's the best proposal you can read. And again, what we can do in the case of these objects, with CanariCam, we can do a spectroscopy in this region to observe, to study the silicates, to determine albedos, to determine size and thermal inertia. That is very, very bad known in the case, in particular, of Sibyllis and Hildus, and study the silicate components. These are the 3 Trojans best observed with the Spitzer, and these are the regions we can observe with CanariCam. Look at the plateau of this silicate emissions. We can do a wonderful job with CanariCam. These objects are very bright to observe this with our instrument. So, with photometry you can do something, but in fact it's easier and cheaper in terms of time to do it with the low res. If you start to put a lot of filters here, you will spend a longer time than just taking a spectrum. Okay, so in conclusion, the aim of our a silica shows an emission high near 10 microns. This is a CIO stage fundamental. The primary goal of our proposal observation is to characterize the surface composition of a sample Cybele, Hilda, and Trojan asteroid based on their low resolution 8 to 13 micron emissivity spectra and N and Q band photometry. If you have the Q band, we can better constrain the thermal model to subtract it from the spectrum. We will measure radius, albedo, and thermal inertia, and combine it with our observations in this spectral range. We will have unique, we will be able to obtain unique mineralogical information of these populations that, compared with similar bubble TNOs, like short period comets, will allow us to test the NIS model. And that's it. Espero que sí.